This unremarkable-looking cluster of industrial buildings somewhere in the southeast of France, a team of engineers is attempting to tackle one of science's most intractable problems: how to summon the power of a star. If they pull it off, they'll solve mankind's greatest existential problems at a stroke, radically reducing harmful pollution and tackling runaway climate change. Still, that's a big if. So join us today as we take a high-energy jaunt inside the world's largest nuclear fusion reactor. Last summer, a critical milestone was reached on a science project so vast in scope it was initiated back in 1985. Because in July 2020, technical construction finally began at the so-called ITER, or International Thermonuclear Experimental Reactor. Situated just outside the sleepy 10th century commune of Saint-Paul-lès-Durance, ITER is the most expensive and complex engineering project ever undertaken by humanity. Its core apparatus alone weighs as much as 3 Eiffel Towers and is expected to cost a cool $25 billion, although cynical estimates put the real figure as high as $65 billion. So what actually is ITER? A global, multidisciplinary team is attempting to build the biggest, most advanced nuclear fusion reactor the world has ever seen. Experts have argued for several decades now that nuclear fusion, if harnessed properly, could provide mankind with a functionally limitless supply of clean, safe energy, with none of the belching hydrocarbon fumes or stubbornly indestructible radioactive waste generated by other less efficient means of power generation. So how does nuclear fusion work? Conventional nuclear power plants rely on the process known as nuclear fission. In a fission reactor, stray neutrons slam into larger atoms, typically uranium or plutonium, causing them to split. This in turn releases energy and even more neutrons, which go on to split still more atoms, causing that dramatic chain reaction we're all familiar with from disaster movies and terrifying old-school footage of ginormous bombs going off. In a regular nuclear power plant, the heat generated by that runaway reaction boils water, which generates steam, that in turn drives turbines in order to create electricity. Fusion, even though the word sounds inconveniently similar to fission, is a different process altogether. In a fusion reactor, 2 or more lighter elements, typically isotopes of hydrogen, are smooshed together to form a larger element, usually helium. This is exactly the same chemical reaction taking place right now in the heart of every star. Fusion is capable of producing 4 times as much energy as fission, not to mention many millions of times the energy generated by grubby old-fashioned fossil fuels. You might reasonably ask at this point why every nuclear power station isn't already fusion-based. Well, for fusion to take place, 3 very difficult conditions need to be met. First, the temperature in the reactor core needs raising to around 150 million degrees Celsius before fusion can even theoretically take place. That's quite an energy-intensive process in itself. Secondly, the so-called plasma in which this reaction occurs needs to be of sufficient density to make fusion a likelihood. And third, this plasma needs to be held in confinement for long enough for the power generated to be usefully harnessed. To this end, ITER engineers are presently assembling a gigantic structure known as a tokamak. This contraption was first proposed by Soviet nuclear physicist Igor Golovin back in 1957. Tokamak, which, since you ask, is a Russian acronym meaning toroidal chamber with magnetic coils, is essentially a vast steel donut where ultra-strong magnets conspire to create sufficient heat and pressure in a vacuum to turn gaseous hydrogen fuel into a plasma. The tokamak at ITER is by far the largest ever constructed. Each one of its 18 D-shaped toroidal field coils, huge magnets in essence, weigh 310 tons, or about the same as a fully laden jumbo jet. That's before we get to its 6 poloidal magnets and this colossal central solenoid that's theoretically strong enough to lift up an aircraft carrier. All this in a tokamak chamber that's twice the size and 10 times the internal volume of anything previously attempted. To keep the largest superconducting magnet system ever running through 100,000 kilometers of niobium tin superconducting wires, the world's largest helium refrigeration unit is being manufactured at the same time. To put all that in perspective, when it's finished, the ITER facility will be home to both one of the hottest places in the universe, 150 million degrees Celsius in the reactor chamber, and one of the coldest places in the universe, at minus 269 degrees C or 4 kelvins in the coolant system. As if summoning the power of a literal star wasn't tricky enough, ITER also happens to be a complex collaborative effort between some 35 nations, each assembling their own parts to be assembled on site. As you might expect, this presents some tricky logistical challenges. Certain individual components, among the estimated 10 million parts that will go into ITER, are being shipped from as far away as South Korea. Some bits weigh 900 tons and others are 4 stories high. A 104-kilometre road from ITER-'s nearest Mediterranean port at Fos-sur-Mer near Marseille has been specially upgraded at eye-watering cost. This multinational endeavour, which takes input from the European Union, United States, Russia, China and India among others, promises stakeholders, in exchange for their support, priceless experimental data and access to any intellectual property generated as a consequence of the project. Construction stage and expects to fire up its first plasma in December of 2025. If all goes to plan, 3 processes will work in concert to raise the core temperature to the magic 150 million degrees C necessary for fusion to occur. These are ohmic heating, created by smart manipulation of those mighty magnetic fields, neutral beam injection of high-velocity charged deuterium, and high-frequency electromagnetic waves, a bit like your microwave at home. And while fusion reactions in a tokamak have been achieved elsewhere, ITER will be the first that generates more energy. Let us know in the comments, and don't